Okay, this is going to be our fourth video in our DC circuit series. Um, this is also going to be our last video in our DC circuit series. I know that the textbook goes on to discuss, let me pull it up here, textbook goes on in section 26.5 to discuss power distribution systems. We're not going to be looking at that section in this course, so this will be our last section for this module. And so we're going to be looking at section 26.4 in this video, and that deals with RC circuits. Okay, and we'll define what those are in a moment here. So far, we've been looking at circuits where all of our EMFs, our resistances, and so forth are constant, and this leads us to currents and potentials and powers that are not changing in time. They're constant as well. We're now going to look at circuits where a capacitor is charged and then discharged, and so our currents, voltages, and powers are going to change in time. Okay, and so if we look at charging a capacitor, well, I guess first off, if we have a circuit with a resistor and a capacitor in it connected in series, we call that an RC circuit. Why do we call it an RC circuit? Well, it's resistance or resistor and capacitor in a circuit, right? So in an idealized RC circuit, we assume that we have a constant EMF and that we have no internal resistance, so our small r is equal to 0. We also ignore the resistance of any of the conducting wires, which is what we generally do when we're doing these types of setups also, right? So we're going to begin with our capacitor initially uncharged. Okay, and we're going to set it up in the setup that we see below here. It's going to start off as we see on the left here in diagram A, with the switch open. And as we close the switch, what's going to happen? Well, we're going to have some current. We're going to have charge starting to build up on our capacitor. Like initially we have no charge on our capacitor, then we close the switch. Charge is going to start to build up on the capacitor, and then after some time it's going to slowly settle down to the point where we have some charge built up on the capacitor and there's no more current flowing, right? So quick note before we get into sort of looking at these systems, quick note on notation. The text uses capital V, I, and Q as we've been using so far for constant quantities, okay? It also uses lowercase v, I, and q for quantities that are changing in time. Okay, and we're going to do the same thing here. I'm going to try to do that also, and as I use these lowercase quantities, I'm going to also sort of put functional notation around it. So for example here, this VAB of t is just telling us that, yeah, it's lowercase, so it's changing in time and it's a function of time. So I use that to sort of double indicate that we're dealing with quantities that are changing in time. These are functions of time. But as we move on, I'm going to probably drop the functional notation and just keep it sort of as clean as we can. Okay. So let's start off looking at this. At a time t equals 0, we're going to close our switch, right? So we have our setup like this. We close a switch, and the instant that we close the switch, we start our stopwatch at t equals 0. At that moment when we close the switch, we're going to have a VAB, or sorry, a VBC, I should say, a potential difference across B and C here. The moment we close it of 0, right? Because there's no charge built up, and so there's going to be no potential difference across BC. And at the moment that we close the switch, we're going to have a potential difference across our resistor, VAB, equal to the potential difference across our EMF source. Okay, so we're going to have a VAB at time 0 equal to the value of our EMF. Okay. Then as the capacitor charges, our VBC is going to increase and our VAB is going to decrease. Okay, so what we're going to end up having is we're going to have our potential difference across the resistor decreasing, our potential difference across our capacitor increasing, but they always have to stand in relation to one another such that VAB plus VBC is equal to our potential difference across our EMF source. So it's equal to our EMF. Okay, and so we have this expression that we're going to make use of in a moment. Okay. After a long time, so after we let this thing settle down for a long time, and we use this idea of long time to mean, you know, a long time period, because all this stuff sort of acts asymptotically, right? So there's no point at which by these equations we're really going to have this thing totally settle down. It'll slowly be settling down as time goes to infinity. Okay, so after a long time, we're going to have VBC as t goes to infinity. Our VBC is going to tend toward our EMF, right? So eventually, all of our potential difference will be made up by the step here over BC, and none of it will be made up by the step over AB. So once this is fully charged, we're going to have all of our potential difference across here. There will be no more current flowing, which we'll talk about in a moment, and we're going to end up with no potential difference across AB and all of it across BC. Okay. Okay, so let's let Q of t, the charge on the capacitor as a function of time, and we'll let this Q of t be that charge, okay, and then I of t is going to be our current in the circuit at some time t. Okay, we're going to choose the positive direction for the current to correspond to the positive direction of our charge flowing onto the left-hand plate. So let's quickly take a look at this again. So we can see that our positive charge is going to come off of our positive terminal, and it's going to flow onto this plate onto the positive side. We're going to call this direction, this counterclockwise direction, the positive direction of our current. Okay, so the current flows onto the plate that way. That'll be our positive direction. Then the potential differences can be written as we see here. Okay, so VAB, so this is just going to be V equals IR as we saw before, and this is just going to be our capacitor equation written down. VBC is equal to Q of t over C. Okay, this is just our Q equals VC expression that we talked about in our capacitor section. Okay. And so if we take these two expressions and we substitute them into what we saw above here, which we talked about how these two potential differences have to always add up to give us our EMF, we can substitute in these two expressions, and if we clean stuff up, move everything over to the left side, and then solve for our current as a function of time, we end up with this expression here. Okay, so this is a sometimes useful expression. This is our current as a function of time. We can see that at t equals 0, we have Q of 0 equals 0, and so our I of 0 is going to be equal to some capital I naught, which is our current at time 0. So this is like our initial current, okay, and it's going to be equal to just our EMF over the resistance, because this term is just going to go to 0 because Q of 0 is equal to 0, right? There's no charge on the capacitor initially, so this term goes to 0, and our current is defined by just this first term. Okay. As we can also see sort of how this sort of acts as time increases. As time increases, our Q of t, the charge on our capacitor plate, increases, and so this second term gets larger and larger as time goes on. As t tends to infinity, we have our Q of t as t is going to infinity tending towards some Q final. So there's some Q final, and this Q final is the total charge that we're going to end up on the capacitor as time goes off to infinity. So we're slowly going to be building up more and more charge, but we're going to be asymptotically tending towards some Q final. Okay. Also, as t goes to infinity, we're going to have our I as t goes to infinity going to 0. And why is this? Well, we can kind of see why this is going to be, because initially we close the switch. There's no charge on here, so charge is flowing. We have negative or we have positive charge flowing onto the plate here this way, but eventually more and more charge flows on, and we're heading to the point where the maximum charge that we're going to get on there is getting approached, and so our current is slowly dropping off, and as we go to infinity, as we have the maximum charge we're going to get on that plate, well, our current drops to 0. Okay. And so we can take this this expression as t goes to infinity. Our Q of t goes to Q final, and our current goes to 0, so we can just shift this term over to this side, and we end up with this expression here. We can also clean up these r's in the basement and sort things out, and we end up with an expression for our final Q. So the final charge that we're going to end up on our capacitor plate is just going to be equal to our capacitance times our EMF. Okay? And so here we have a couple of plots. I made them maybe a little too small, but we have a couple of plots of what the current over time looks like as we're charging this capacitor, and what the charge on the capacitor plate over time looks like as we're charging the capacitor. We can kind of see this exponential decay here in the case of our current, so it's slowly dying off as the capacitor plate charges, and we can see that the charge on the capacitor has this behavior where it's asymptotically approaching Q final as we move forward in time. Okay. Now we want to really generate the sort of equations that give us these plots, and that's the sort of next step that we're going to work on here. We can derive the sort of general expression for Q of t and I of t. We're going to start out by looking at I of t. So I of t, our current as a function of time, is just going to be the time rate of change of our charge as a function of time. Okay. So then from equation 2, which we had above here, just flash that on the screen here quickly. So from equation 2, we can write our I as dq dt, write it down like this. We can simplify the right hand side a little bit. We'll factor out an RC in the basement from both. And then what we're wanting to do here is we're just wanting to gather all of the Q terms on one side and all the T terms on the other side. And after we do that, we're simply going to integrate both sides. Okay, so we're going to relabel our dummy integration variables as Q prime and T prime here, so we free up Q and T to be used as our limits of integration. They're going to be our upper limits of integration, and our lower limits are going to be 0 in both cases. We'll do the integrals that we see here in equation 6. We're going to get the result that we see here. We're then going to exponentiate both sides, so we'll take e to the power of all this stuff and e to the power of all this stuff. When we do that and clean it up, we end up with this expression here. And what we're really interested in is getting our charge on the capacitor plate as a function of time and our current through the circuit as a function of time. So we're going to solve, starting off, we're going to solve for Q, so we're starting off looking at our charge on the capacitor plate as a function of time. If we solve for Q, we end up with this expression here, and we can substitute in for this term, which we just talked about above. This capacitance times our EMF is actually equal to the final charge on the capacitor, which we write in this way. This expression, 26.12 here, this is an important one that's sort of, I guess it would be boxed, but it's really just written in this way because I copied it from the textbook. I like the way they sort of discuss all the terms there. And so this is one expression that we're definitely going to want to remember, and it'll be on the formula sheet. How do we get our current as a function of time? Well, we simply take this charge as a function of time, and we talked about how the current as a function of time is just going to be the time rate of change of our charge as a function of time, and so we have that here. It's just dq by dt. We do the derivative, clean things up, and we end up with this expression here. And this I naught, this is our initial current. This is the current the moment that we close the switch and the charge starts to flow through the circuit and deposit charge on the capacitor plate, right? And so this is our expression for I as a function of time. Okay, and if we were to plot both of these, we would end up with the plots that we saw up here. They're kind of in inverse order. This is our charge as a function of time. This is our current as a function of time, but those are the plots for these two equations that we see down here. Okay, we're going to do some examples working with these, but these are both going to be important for us to be able to solve problems. Okay, so let's talk about the time constant. So after a time t equals RC, okay, and RC here, this is our resistance, our external resistor there, and C is our capacitance on our capacitor. The current in the RC circuit has decreased to 1 over E of its original value, And the capacitor charge is now 1 minus 1 over E of its final value, so that the final value being QF, which is equal to C times our EMF. We call this product, this RC product, the time constant, or the relaxation time of the circuit, and it's measured, it's kind of used to measure how quickly the capacitor charges. So we give it the symbol tau, so we set tau equal to RC, and tau tells us how quickly this capacitor is going to charge. A small tau means the capacitor charges very quickly. A large tau means the capacitor charges very slowly. And we can kind of see that because we can imagine, well, what would give us a large tau? Well, a large R would give us a large tau. That would mean we'd have a large resistance. And if we have a large resistance, it takes more time for the charge to work its way across the resistor. Our current will be smaller, and so the capacitor will charge up more slowly. Well, what if instead we had a large C? Large C means that we have a very well, we can think of it like a parallel plate capacitor. We have large plates. We can store a lot of charge on there, so it takes a lot of time for the current to deposit all that charge on those plates, right? So again, small tau means quick charging. Large tau means slow charging. Okay. We're going to make use of this tau as we move forward, but you often see this collection of two variables, this RC, and so they're just given this symbol tau. Now we're going to take a look at discharging a capacitor. So now let's suppose that the capacitor has been charged and it acquires this charge Q0, okay, and we remove the battery from our RC circuit. So we can see basically this is our RC circuit from above. We had the battery. Where is it? We have the battery in here, right? So we have the battery in here, but now we're going to pull out the battery, and we're left with this situation here. So we have no battery, the switch is open. So we have no battery, switch is open, the capacitor is charged. We call the initial charge on it now Q0 because we're resetting our stopwatch to 0 again after this thing is charged. So we call this Q0, battery is removed, and we connect these 2 points A and C to this switch, like I said before, right? We're then going to close the switch, right? As we set our stopwatch to 0, and we're going to kind of see what happens. Okay, so our Q of T, the charge on the capacitor plate at the moment that we close the switch is still going to be equal to Q naught. So that's our initial Q. Then the capacitor is simply going to discharge through this resistor. Our Q is going to slowly go to 0, right? The positive charge is going to run around the circuit here. It's going to run through the resistor, and eventually we're going to end up at the point where we have our capacitor fully discharged, right? So we kind of have that all laid out here. Open switch closes, charge is going to run around this way, and so we still have the same labeling scheme, right? We still have current running in this direction, but we're going to find that our current is actually negative, and so the current, our positive charge, is going to run around in this direction. Okay. So let's take a look at how some of that is going to work here. We're going to keep the same sort of labels and conventions from what we did above, but now we've pulled out the battery, right? So if you remember, there used to be another term here for our I as a function of time, but that term depended on our EMF, and now there is no more EMF. We pulled that out, and so I is simply equal to the collection of terms that we see here. Okay, and note again, our I is negative, and that's because we're going to have our current actually flowing against the direction that we previously set our I to be, right? And it was a good choice of I originally, because originally when we had the battery in here, the current was running like this. But then as we pull out the battery and switch the switch closed again, and let the charge run around the circuit, our current is going to be in this direction because positive charge is moving across sort of against the direction it was when we originally set our current direction. Excuse me. Okay. So I is now negative, as we talked about. The charge is leaving the left-hand capacitor, and it's moving around the circuit. At a time t equals 0, we have Q equals capital Q naught, and I is going to be equal to our initial our initial current, which is going to be equal to this value here, which is simply this with our Q naught substituted in here. Okay. To find Q as a function of time, we're simply going to do what we did above. We're going to move all the Q terms to one side, all the T terms to the other side, and then do a very simple sort of integration like we did before. We're going to be integrating from, instead of from 0 now, we're going to be integrating from Q naught, because we start off with some initial charge, and then at some time in the future we'll have charge Q, and we're starting from 0 in the case of T, where we're starting our stopwatch at 0, and it runs to some time T when we want to take a reading. Okay, so we do this integration, we end up with this result here, and again we're going to do the whole exponentiation thing. If we do that for discharging our RC circuit, these are the two equations for our charge as a function of time on the capacitor plate, and our current running through the circuit as a function of time, both of which are now for the discharging of this capacitor in the RC circuit. Okay, the previous ones were for charging, these ones are for discharging. Okay, we can see the two expressions here. This one is not too bad. This is what we end up with over here. This is our initial current. This is our initial charge on the capacitor plates, and we end up with these terms here. This RC term can also be written as tau, and we'll sort of do that in the examples that we take a look at in a moment. Okay, so we can plot the two of these expressions again, and we end up with plots that look like this. So we can see our current here. We start off with a 0 current, then the switch is closed at t equals 0. Right away we get the maximum magnitude for our current, but again our current is negative, right, because it's pointing in the other direction. And we see the current starts off at this largest possible negative value and then slowly goes to 0 asymptotically as t goes on, right? And sort of a similar but opposite situation for the charge on our capacitor plate. Our capacitor plate is charged, it's charged, and then we close the switch, and so it starts to discharge right away. Charge is running off the capacitor plate, and it's tending towards 0 here as t goes to infinity. Okay, so those are the two setups that we have in the case of discharging our capacitor. The last thing we want to look at before we look at a couple of examples is energy in RC circuits. And so if we look at the sort of energy in an RC circuit, it can give us some additional sort of information of what's going on there. We know that while the capacitor is charging, our battery is delivering power to the circuit. The power that it's delivering is equal to P, which is equal to our EMF times the current at that moment in time, right? And we also know that energy is being dissipated in the resistor at a rate shown by this value here. This is the energy being dissipated in the resistor. And we also have energy being stored in the capacitor, which is equal to this value and this value also. Okay, this is some of this stuff you'd have to look back at the work we did in the capacitor section for these things to see where we sort of derive them from. But if we put all this together, the power being supplied by our battery has to be equal to the power being dissipated in the resistor plus the power being stored in the capacitor, right? And that's this expression here. We may find this expression useful to use. Maybe I'll box this off. May find this useful to use in some of the examples. Okay, and the last point I want to make here is that the total energy supplied by the battery during the charging is going to be equal to our EMF times the total final charge that we're going to have built up on the capacitor. We know from our earlier work that the energy stored in the capacitor, and again we'd have to go back to our work in the previous chapter on capacitors. We would see that the total energy stored on the capacitor is actually equal to half of this amount. So we're storing half the energy that's put out by the battery and the capacitor, and that means that the other half of that energy has to be dissipated by the resistor. Okay? And so those are just a couple of useful facts that we can sort of garner by looking at energy considerations for these RC circuits. All right, so I have two examples. These are exactly the examples they do in the text. So we'll do the two examples from the text. We'll take a look at how some of this works, and then we will move on to the next chapter. So this is example 26.12 from the text. It's the charging of a capacitor. We have a 10 to the 7 ohm resistor, which is connected in series with a 10 to the minus 6 farad capacitor, and an EMF source that's putting out 12 volts. The switch, so we have the same setup that we have above here. I didn't bother to redraw it, but we have the same setup from way up over here. This setup here. So the switch is then going to be closed at a time t equals 0, and the capacitor is uncharged at that point, but it's going to start charging at that time. Okay. So first thing we want to know in part A is what is the time constant. Okay, so this is very, very easy. We just go to our expression for the time constant. We know that the time constant, written as tau, this is the Greek letter tau, is equal to RC. We can just take the values directly from above here. It's just going to be 10 to the 7 times 10 to the minus 6, and this is going to give us 10 seconds. That's going to be equal to our tau. Okay, so this would have been 10 to the 7 ohms, 10 to the minus 6 farads. If you do the calculation, you're going to find that that you end up with units of seconds, but in the end we know that this has to be seconds because tau is a measurement of time. So tau is a specific time that we give the value RC to. Okay, so we found our time constant here. Okay, part B, we want to know what fraction of the final charge QF is on the capacitor at a time t equals 46 seconds. Okay, so we're interested in sort of what's happening at t equals 46 seconds. In part C, we're also going to want to look at what fraction of the initial current, our I0, is still flowing at t equals 46 seconds. Okay, so everything's going to be happening at t equals 46 seconds. Okay, so for part B, we're gonna use equation 26.12. Okay. Equation 26.12, and I won't scroll up to it, but it's basically our expression for the charge as a function of time on the capacitor plate as it's charging. And so we have this expression from above. Okay, looks like that. And what are we really interested in? We're interested in the fraction of the final charge at the time t equals 46 seconds. So we're really interested in Q, small q, over QF. Okay, and this is equal to, we can see right from here that this is going to be equal to 1 minus e to the minus t over RC. But RC we know is just tau. So this is just going to be 1 minus e to the minus t over tau. Okay, and now we just need to substitute in our values. Okay, so we have 1 minus e, and our t is 46 seconds, so we're going to have minus 46, and our tau is 10 seconds, so it's just going to be 10. So this is just going to be 1 minus e to the minus 4.6. Okay, if you do that calculation, you will find that this is equal to 0.99, right? And so this is our fraction Q over QF. Okay, this is the fraction of the final charge that's on the capacitor at 46 seconds. Okay. Let's now take a look at part C. In part C, we are looking for the current at that time. So we're going to use equation 26.13 here. Equation 26.13 gives us I equals I naught. This is our initial current times E to the minus T over RC. But again, we can well, okay, so first we're looking for the fraction again. So we're really looking for I over I naught. And that's just going to be equal to e to the minus t over RC. But we know that we can write this as e to the minus t over tau. And we have these numbers worked out, right? So this is just going to be equal to e to the minus 4.6, right? The same thing we had above here. Okay, so if we do that calculation, we can see right away that this is going to end up giving us 0.01, and this is equal to I over I naught. Okay, that's the fraction of the charge still present at 46 seconds of the initial charge still left at 46 seconds. Okay, so that's the first example. Let's take a look at the second example. In the second example, we're dealing with the same setup that we had above, but we're now discharging the capacitor, and we're given some additional information. So the resistor and the capacitor from the previous example are left in series. The EMF source is removed, and the capacitor has an initial charge of 5 times 10 to the negative 6 coulombs, and it's discharged by closing the switch at t equals 0. So we're resetting. So we basically charge this thing up, we open up the switch, remove the battery from the circuit, connect everything back up, reset our stopwatch, close the switch, and start the stopwatch at t equals 0. Okay. Now we want to know at what time will the charge be 0.5 times 10 to the negative 6 coulombs. So when will it be 1/10 of what it was originally? So that's what we want to solve at first in part A. So in part A, we're going to use equation 26.16. This is one of the equations for the discharging of our RC circuit, the discharging of the capacitor in our RC circuit. And so what does this equation give us? This gives us Q equals Q naught, our initial charge when we're about to close the switch, times e to the minus t over RC. We want to solve this for t. Okay, so we want to know what the time will be when the charge reaches this amount. So we need to liberate this t from in here. To do that, so we're going to solve for t. So if we do that, we're going to take the natural log of both sides of this thing. Maybe I'll do a few steps here. We'll do ln q is going to be equal to ln of big Q naught minus t over RC. Okay, so that's what we get if we take the natural log of both sides and clean things up a little bit. We're going to move those two logs to one side. We're going to end up with something like this: minus t over RC equals ln Q over Q naught. Okay, so remember your rules when you're dealing with logs. This RC here, this basement here is just tau, right? So we can make that simplification. We'll move it to one side. We're going to end up with t equals minus tau times the ln of q over q naught. Okay. We can substitute in numbers for this. We know what q naught is. We also know what q is. We're told that it's 1/10 basically. So we can substitute in the numbers, but we can see, or maybe I'll just substitute in the numbers rather than making a leap here. So we can see that this is just going to be ln of 0.5 times 10 to the minus 6 over 5 times 10 to the minus 6. And so this is just going to end up being ln of 0.1. Okay, and the ln of 0.1, if you feed that into your calculator, is minus 2.3. Okay, and so if maybe let me finish it off here, but I'll clean it up over here. So we're going to have a t equals minus tau times minus 2.3. Okay, and if you now put in our value for tau is still 10 seconds. So we're going to end up with a t, and then the minus signs cancel. Obviously, we're going to end up with a t of 23 seconds. Okay, so what is this telling us? This is telling us that at a time at the time 23 seconds, we're going to end up with a charge of 0.5 times 10 to the negative 6 coulombs, where we started off with 5 times 10 to the negative 6 coulombs. So 90% of our charge will have left our capacitor at 23 seconds after it's hooked up. After the switch is closed. Okay. Now I'm going to do part B. I'm a little scared that this thing is going to crash. I haven't saved it, but actually let me pause and save it. One sec. Okay, let's finish this off. In part B, we are looking at what is the current at that time. So we want to find the current at 23 seconds, right? So we're going to be looking at the equations for discharging a capacitor. This is going to be 26.16. 17. That's the equation we're looking at. We want the current. It tells us that I is equal to minus Q naught over RC, e to the minus T RC. Okay. Both of those RCs can be turned into taus, so we'll just do it right away. We'll do minus Q naught over tau, e to the minus T over tau. Okay, and at this point we can just substitute in numbers. We know what our tau is. That's just 10. We know the Q naught. We're told what that is. So let me just start writing in the numbers. We'll have minus 5 times 10 to the negative 6 over 10 e to the minus 23 over 10. Okay, we can clean this up. Maybe I should have added a page here, but we'll work with it. And so we're going to end up with an I equal to, it's going to be 5 times 10 to the minus 7, and e to the minus 2.3. If you do e to the minus 2.3 in a calculator, you will find 0.1. And so if you do that calculation, you'll find an I equal to, oh, and I'm missing a minus sign. There should be a minus sign here. We're going to end up with minus 5 times 10 to the minus 8 amps. Okay, so that is the current in our circuit as it continues to discharge at that moment at t equals 23 seconds. Okay, so those are two examples from this section. This is sort of maybe one of the more important sections in this chapter. I would say this one and the section on Kirchhoff's rules are both very important. So if you're focusing on stuff to study, I would say do extra examples from those two sections, okay? So we'll leave it here for this chapter, and in the next video, we will start off the next chapter.